Welcome to the ET302 how-to video for the DC Power Supply Lab. Here we are at Multisim, and this is our first file. First thing we need to do is download our zip files and unzip them and go from there. And if you're using the VMware, go ahead and get them off the instructor files. So let's start this file. So here's our sine wave, and let's go ahead and bring down a bit, and let's pause it. That's close enough right now. So what we have is a AC generator sine wave, 20 volts peak at 60 hertz. Into our oscilloscope, and we're going to show you the difference between a DMM measurement and a oscilloscope measurement. So here we have, if we look here, we have, let's go ahead and go between the two, and we're measuring the peak to peak on this. So we should have 20 volts peak, and we do 19.967, close to 20. And here's our negative peak, which is minus 20, and we have a total peak to peak of 40. Okay, so even though we have that, so let's go ahead and measure our RMS. So let's go to AC. There we go. And we have 14.1 volts. So RMS is an average of our AC sine wave. So we're taking area under the curve and area under this curve and going through some math, and it's about 1.4 times the peak, and that we're coming up to 14, and that's our average volts. Okay, so if we try to measure DC on this, it's going to be 0. And here we have bouncing between microvolts. So it's pretty close to 0. So what we're doing is we're measuring the positive and negative. And since they're equal pretty much, we're going to zero out. So if we use a DC meter to measure voltage on AC, it's going to go to 0. Okay, let's go to our next file, and we don't need to save this. Let's go ahead and open it up, and let's go to this desktop, and let's open up this guy. And here we have a half wave power supply, a simple one. It's unfiltered. Okay, so we have 10 volts peak, 20 volts peak to peak, standard 60 hertz. Our transformer is a 1-to-1, so we should get the same voltage out. So let's go ahead and start it and open up our oscilloscope, and let's pause it. Never pauses when I want it to. Good. So what we have is our AC sine. Okay, so here we have a half wave output. Okay, so this produces a lesser voltage. Okay, because we have to backfill in between these sine waves. So the diode, the rectifier, is blocking the negative sign. And let's see here, if we go ahead and turn on our AC, that is our input. Okay, and you see the blue's a little bit smaller. Well, that's up because of the 0.7 or 0.5 volts drop across our rectifier. So that's normal. So let's go ahead and block that. But that is a normal half wave signal. Here I'm back at Multisim, and I've opened up a new file that's not in the lab but probably should be. What I have here is a full wave rectifier. So it has two diodes and a center tapped transformer. So the problem with the center tap transformer, they're a little more expensive and it cuts the voltage in half. So it's not as efficient as the next one I'm going to do, which is a bridge rectifier, but this one shows a good half wave signal. So here we have our signal. So let's go to DC and let's go ahead and go to a single. There we go. All right, so what we see here is with a full wave bridge, here's our sine wave, and one goes positive. The other diode, which is on the other side of the transformer, is going to take our negative sign and put it on top. So now what we have is a wave that's easier to filter, and we get more out of it and a cleaner signal. Again, we're losing a lot of the voltage because of our center tap. We're only here at 4 volts, but that is a full wave rectifier. So let's shut this down and open up our next file, which should be a B2, but on mine it's going to be just plain B. Okay, here we have a full wave bridge rectifier. So we have 4 diodes in there, and the reason we use these is we don't require a center tap, so we get double the voltage out, and these are pretty inexpensive and they come in an integrated circuit form. So this is the way that a typical positive power supply would be made, and if we want a negative, we're just going to come off of this side and use that as our negative output. So let's turn her on. And here's our oscilloscope, and what we're going to see is it doesn't show us that half wave form that we showed on our other one because of the configuration of our diode. So let's go ahead and open it up, and here we have 8 volts out, almost twice of what we had on the other one. This is an unfiltered. Okay, so we're getting about 8 out. Okay, let's open up our next file. And it is going to be P3A. Let's get rid of that. There we go. So what we have here is we're back to our half wave rectifier. This time it's filtered. Okay, so we have a 100 microfarad capacitor, and that allows us to filter a DC power supply. So let's start it and get our signal over here, and let's go to single, and let's take a look at our voltage. So right now we're getting 13.7 volts out, which is very good, and that is because we've captured the area in between the two. So let's go ahead and turn on our AC. So here's our sine wave. Okay, and what the capacitor does is it backfills this area here. So between this wave and the next wave of our half wave, it fills that in and smooths it out and filters it. This is called ripple. But anyway, with this capacitor, we're able to filter the DC out of this. Okay, and the larger the capacitor, the better we're going to get. So let's go ahead and go to 1,000 here. And you see how smooth that is, and we got more voltage at it. So the larger the capacitor filter, the smaller our ripple, and the better the DC and the higher the voltage is out. So okay, let's go ahead and shut this down, open up our last file. And what we have here is a full wave bridge filtered. So let's go ahead and take a look at it. And let's do a single. And you could see that here's our ripple. And if we open up our sine wave, we see that we're getting both sides of the sine, positive and negative, on the top, and it's filtered. Let's go ahead and add a meter here. And see what kind of voltage we're getting out. And we're getting 15 volts out of here. DC. This is a typical power supply. So let's go ahead and do the same thing. Let's go ahead and make this 1,000. Much smoother. Looks like we got more voltage out. Good.